Welcome to this explainer. Today, we're diving straight into what is absolutely, hands down, the biggest headache in modern hardware engineering. We're talking about power consumption in the Internet of Things, and this is your complete guide to low-power design.
Okay, to start off, just picture this for a second. There is a little sensor buried under a massive cornfield out in Iowa. It wakes up, checks the soil moisture, and wirelessly transmits that data every single hour. And it's been doing this for 8 straight years. Literally no one has touched it since the day it went into the dirt. 0 battery changes, nothing. So how on earth is that even possible? How does a piece of electronics survive almost a decade out in the middle of nowhere on a single charge? Well, that's exactly what we're going to figure out today.
To really grasp why this matters, we have to look at the sheer scale of the situation. By the end of 2025, experts project we'll have around 18 billion IoT devices connected worldwide. And look, we're not just talking about the smart speakers sitting in your living room. We are talking about sensors on oil pipelines in the tundra, heart monitors on patients, and tracking devices on cargo ships in the middle of the ocean.
Which brings us to Section 1, the IoT Power Challenge. Billions of devices, remote locations, high stakes. So here is the core constraint. Most of these billions of devices are going into places where you just can't easily reach them. Replacing a dead battery isn't just slightly annoying, it's a massive logistical nightmare that can actually cost more than the sensor itself. Poor power design leads to dead devices, ridiculous maintenance costs, and completely failed projects. And that's a really big deal in a low-power IoT market that's globally valued at over $7.8 billion. I mean, think about your laptop for a second. It has a massive battery, right? Plus, it's usually sitting a few feet away from a wall outlet. But a remote IoT sensor? A lot of these things are running on a tiny CR2032 coin cell. That's a tiny little battery holding a meager 240 milliamp hours of juice. Even the bigger ones are just small lithium-ion packs with maybe 500 to 3,000 milliamp hours. You're basically asking engineers to squeeze years and years of life out of the energy equivalent of a single AAA battery.
So where is all that precious energy actually going? Let's get into Section 2, 3 major energy drains in IoT devices. It helps to kind of personify the device here. First, we have the brain, the microcontroller unit, or MCU. Now, modern MCUs are pretty brilliant. They can draw mere microamps when they're in a deep sleep, but the second they start actively processing, that spikes up to several milliamps. Next, you have the eyes and ears. Those are your sensors. And finally, you have the mouth, the wireless communication module that's constantly trying to talk to the network.
Let's talk about those eyes and ears first. If you program an always-on temperature sensor to continuously poll the environment every single second, basically asking, is it hot now? How about now? Now? It is going to completely kill your battery in no time. It's a massive energy drain. Instead, the real trick is using event-driven activation. The sensor essentially stays completely asleep and only taps the brain on the shoulder when a specific threshold is crossed. You know, like if there's a sudden temperature spike, or maybe a machine starts vibrating when it definitely shouldn't be.
But honestly, the biggest culprit by far is the mouth. Sending data wirelessly is universally the most energy-intensive thing an IoT device does. And here's a totally wild fact from security research. If you want to send a tiny little 10-byte payload of temperature data, it can actually require thousands of additional bytes just to handle the network security and the encryption overhead. Because of that tax, engineers have to ruthlessly optimize their data payloads. By using data compression, they can actually slash transmission times by up to 80%.
Let's move to Section 3, the power of sleep modes, the core survival technique. Okay, so if thinking and talking take up so much energy, how do these tiny devices survive for a decade? It all comes down to a mathematical concept called the duty cycle. It's basically the fraction of time a device spends awake versus asleep. If your device has a 1% duty cycle, it means it's only active for about 8.6 minutes out of an entire 24-hour day. The rest of the time, it's out cold. By aggressively duty cycling, we drop the effective average current down to practically nothing, mere microamps. To put that into perspective for you, a device that would normally drain its battery completely in just 2 weeks of continuous running can easily last over 10 years if you duty cycle it right.
And there's an entire hierarchy to how they sleep. Modern microcontrollers are honestly like master yogis. They can slow their heart rate down in distinct stages. They step down from idle, where just the CPU is turned off, into light sleep, then down to deep sleep, and finally hitting rock bottom in hibernate. In hibernate, the device sips as little as 0.1 to 1 microamp. When protocols like Bluetooth Low Energy, or BLE, go into deep sleep, they pull a tiny 1 to 10 microamps, and Zigbee can drop down to just 1 to 5 microamps.
Which leads us nicely into Section 4, Wireless Protocol Trade-offs, choosing the right language. Picking the right wireless language completely defines your power budget and your range. There's really no magic one-size-fits-all here. It's a massive game of trade-offs. This is essentially your cheat sheet. You've got Wi-Fi, which gives you incredible bandwidth but burns through power like crazy, so totally a no-go for remote battery sensors. Then you've got BLE, which is perfect for wearables and has a range of about 10 to 200 meters. Zigbee is incredible for smart buildings because it forms a mesh network where devices pass messages along to each other. And then we get to the long-range titans. LoRaWAN can give you 15+ years of battery life and up to 50 kilometers of roll range, so perfect for agriculture. And NB-IoT uses existing cellular towers, giving you 10+ years of battery life, making it an absolute powerhouse for urban environments.
Now, comparing those two heavyweights, LoRaWAN and NB-IoT, they're both fantastic LPWAN options. But here's the key insight. LoRaWAN actually consumes slightly less power than NB-IoT when it's in its sleep state. And that extreme, obsessive level of energy efficiency makes LoRaWAN the absolute favorite when we start talking about getting rid of batteries entirely.
And that takes us to Section 5, Batteryless IoT and Energy Harvesting.
We are looking at a fundamental paradigm shift in engineering right now. Traditional IoT is totally reliant on a stored, finite tank of energy, the battery. But energy harvesting, that is all about converting ambient environmental energy into infinite electrical power. When you pair this with an ultra-low power protocol like LoRaWAN, research is actually showing that under the right conditions, perpetual, forever operation is entirely achievable. No more battery replacements.
So where are we pulling this free energy from? There are 4 main harvesters. You've got solar, using tiny panels for outdoor sunlight or even indoor artificial light. You've got thermal, which harvests the temperature difference from things like a hot industrial pipe. Then there's kinetic, which I think is just brilliant. A vibration sensor on a factory motor can literally be powered entirely by the shaking of the motor itself. And finally, RF harvesting, which is more experimental, but it captures ambient radio waves from local Wi-Fi or cellular networks to trickle charge the device.
Let's look at what's next in Section 6. Edge AI and Future Trends. Enter TinyML.
To make those batteryless devices truly viable, we have to desperately cut down on the amount of data they send. Remember, the mouth is the biggest power drain. Traditional IoT senses everything and clumsily uploads all that raw data to the cloud. Edge AI totally flips the script. Modern chips from companies like Qualcomm, ARM, and STMicro can now run sophisticated machine learning models locally, pulling less than 1 milliwatt of power. The device does all the thinking locally. Instead of continuously streaming raw vibration data, it just sits there, processes it, and only sends a tiny ping saying, hey, this machine bearing is going to fail in 2 weeks. That simple change results in a massive 10 to 100 times reduction in power-hungry wireless transmissions.
And the real-world results we're seeing from combining all these strategies are just incredible. A 2025 research framework study showed that implementing these energy-efficient IoT frameworks reduced overall energy consumption by about 35% and improved device lifespans by up to 33%. We're seeing it everywhere. In agriculture, LoRaWAN soil sensors are running for years. Healthcare BLE wearables are monitoring glucose and heart rates for months. Smart cities are using NB-IoT for waste management with zero maintenance. We're also seeing specialized gateways taking on the heavy lifting of security, shielding those tiny edge sensors from power drain. And the market is just exploding. The IoT battery-based Wi-Fi market is projected to reach 1 billion units by 2025, and LPWAN is expected to connect over 2 billion devices shortly. Which leaves us with a truly exciting thought to wrap up this explainer. With the fusion of ultra-efficient sleep modes, localized edge AI preventing unnecessary transmissions, and our new ability to harvest perpetual energy from the sun, heat, and vibration, are we rapidly approaching the end of the battery replacement era for good? Could the future of the Internet of Things be a completely self-sustaining, batteryless web of intelligence just seamlessly woven into the fabric of our world? It is a wildly fascinating prospect, and IoT engineers are making it more of a reality every single day. Thank you so much for joining me on this deep dive. Keep exploring, and I'll see you in the next explainer.